I'm pretty sure it's like illegal.
It's in both.
It's not like you have all the audio in one.
Yeah, exactly.
I'll double check.
For like graded stuff, you need to get it back like computation protocol. It's like a regulation.
Of course. Yeah, of course.
But I don't trust anyone showing the truth now.
I mean, like, it's okay if it's just like one thing, probably happens all the time. But like half of the class, like more than half of them are not graded.
All right, I'm gonna get started.
By the
Thanks.
time you finally.
There's snacks here if you want.
Might have converted it.
Okay, today's last lecture.
Is your mic on?
Oh yeah, maybe it's off. Wait, how is it now? It's good? All right, thanks, Dave. All right, today's the last lecture. It's about quantum supremacy. I don't have a lot to write on the board, so I'll just sit here and talk for most of the lecture. Yeah, so let's see. So quantum supremacy is like a term coined in about 2012 by John Preskill, and it refers to like a very specific concept. The concept being like getting an actual real-life quantum computer to perform some task, some computational task, that's believed to be impossible to perform by any real-world classical computer. And it's kind of in the news these days. I mean, you hear like this phrase being spoken, and perhaps people will even claim to achieve it in the next, I don't know, year or something. So I thought we could end the course by talking about this concept, and then you'll be perhaps well informed to judge about potential claims of quantum supremacy being achieved. Yeah, by the way, I'm not like a huge fan of this term. Like, it's a little distasteful sounding somehow. It's got pluses and minuses. It's kind of catchy, I guess, and there's like no other like shorthand term that like exactly describes this particular concept. So I guess we have to stick with it. Yeah, and again, this particular concept is just the concept of building like a real-world quantum computer with maybe, I don't know, like 72 qubits and like 1,000 gates that does something. And then to assert also at the same time that no classical computer, like supercomputer, like that fits in the universe, could do that same something. And they don't care if that something is useful at all or anything. Just anything, any like computational task, if they can do it with like a quantum computer in the real world and also argue that a classical computer could not do it, then they'll say, quantum supremacy, we did it. Perhaps like one of the most likely teams to like try to do it and or announce it in the near future is this team led by John Martinis, who is like formerly of UCSB, maybe still affiliated there and now like working at Google. And particularly they have a paper with like Nevin and Boyshow and others where they like really explain their plan. This is from like a year ago maybe for achieving quantum supremacy. So I'm going to tell you a little bit about that specific plan as well. And you might ask, like, what is this something that they're going to do with a quantum computer that cannot be done with a classical computer? And it's simulating a quantum computer, which sounds like cheating. Some naysayers think that's a little bit bogus, like just it's going to be a computer that simulates itself, or it's going to implement a random quantum circuit. I'm on board though. I'm on board the hype train. I think if they can do it, it's not cheating. It's cool. It'll be great. So we'll find out. But first, before we get there, I want to talk a little bit about stuff that we didn't get, unfortunately, that much time to talk about, which is the question of, why don't we just have large-scale quantum computers right now? In particular, if we did, then we would just implement Shor's algorithm, and that would be real quantum supremacy. I mean, we've implemented Shor's algorithm, can't do it with a classical computer. It would be amazing. Well, it's an engineering challenge, I guess. I mean, it's very hard to isolate a qubit and prevent it from getting noise and decoherence and corruption or whatever you want to call it. In particular, it's got to maintain its entangled state with lots of other qubits. So this is very challenging. In fact, another way to put it is it's hard to implement the 0 qubit gate that does the identity. Just the gate that does nothing. Just holding on to a qubit state and letting it exist for a little bit of time is hard. So that's obviously the first thing you need to do if you're going to build a quantum computer. As far as I know, implementing a 1 qubit gate or a 1-qubit measurement gate is like not that much harder. But even harder is implementing like a 2-qubit gate, like even a C0 gate is very challenging. It makes sense because I mean you got these 2 qubits, they're physically objects, to make them interact in like a careful way, but like also like not accidentally measure them so that they like actually change their state in the way they're supposed to. So obviously that's tricky. That's an even harder engineering challenge. As an aside, I guess you also have to like physically lay out the qubits. Like these are physical particles, and the most common setup, by the way, is I guess in like a 2D grid. Like a 2D grid of particles. And so that's actually also further constrains you because physically you can only do the C0s. Let's say you're going to implement a 2-qubit C0 gate between like grid adjacent pairs of particles. Luckily though, that's fine. I mean, it's not too hard to prove a theorem that says like, okay, if you have your qubit, you know, we always drew them just like horizontal wires and we could put like the gates wherever we wanted. But if they're actually arranged in in a 2D grid, and you only allow yourself like 1-qubit gates and like 2-qubit C0s that go between grid adjacent qubits, then that's fine. That's actually sufficient in theory to do full-scale quantum computing. So that's good. But just as I said, you know, getting a circuit to like last for like a short amount of time, you know, through the length of time it requires to apply like, I don't know, a dozen gates to it, is hard. And indeed for real-world practice, I'm going to draw a little bit on the board. You know, so far we've mainly been drawing like circuits and counting their gates, but I guess like parallel time is a little bit more important these days. So, so you have the qubits, and I guess they're going to be arranged in a 2D grid, like maybe you have 16 qubits. And right, so then, you know, the first time instant, maybe you leave some alone, maybe you apply some 1-qubit gates to some of them, different kinds. And maybe you apply like some C0s to a couple of adjacent ones. Okay, and you do that in like the first round, and then like in the next time slice, you have the same qubits, and you can do like some different gates, etc. to them. Okay, and oops, that's not a parallelogram. Okay, maybe you keep doing this for like a few rounds, and then maybe by that time like your qubits all die or decohere. Perhaps you have like measurements at the very end. Okay, so perhaps that's what, you know, the kinds of circuits they're trying to build these days with some small number of qubits. And just getting these qubit states to like be coherent for this long is the challenge. So in fact, I want to say that like, you know, you hear stories these days about, oh, like IBM built a quantum computer with like 25 qubits, and then somebody else built it with like 50 qubits. That's actually 49 qubits because it's a 7x7 grid, but they just rounded up to 50. Or like Google's, you know, built some quantum computer with like 82 qubits, which is like 8 times 9 grid. That's fine, but like the bigger issue, is, from what I understand, is getting just like a high quality qubit and like high quality implementations of gates, you know, so that these bits can like last and you can actually operate on them. So this is like more important than maybe the raw number of qubits you have. Right, now actually on the subject of, you know, like noise and worrying about like an perfect implementation of a gate, or like that, you know, like your qubit will just decay. Actually, this is an issue that people worried about in the original days of actual, you know, the normal classical computers, like in the 40s and stuff. They were building it with, I don't know, vacuum tubes or whatever, or latches, and they were worried about like the failure of gates there too. So actually this issue of like, can you make computations like fault tolerant to noise has been around for a while. And yeah, let me write a little bit something on the board. Like the model they studied there is also a model studied in quantum computing these days. Maybe you imagine that like each gate that you have, imagine you're trying to build like an and or not gate to compute something. Each gate fails, you know, independently with some probability, eta for error, greater than 0. When I say fails, you can just imagine that it outputs, you know, garbage. Maybe it outputs the wrong answer. Maybe it outputs like a random answer. Just, in fact, any adversarial thing can happen, we'll assume. And you might ask, you know, can we still achieve like full-fledged classical computation if you're worried about this? So they thought about it, but actually it turned out that like it didn't end up being like a really important question, because their implementation of the classical computers, the qubit or the bits, turned out to be really good and not that error-prone anyway. And one reason for that you can imagine is, I mean, okay, if you think about a circuit, like a bit is either a 0 or 1, and maybe it's represented like by a voltage on a wire. So you're really whether it's like high or low, you're really using like 1,000,000 particles, like electrons, to store like 1 bit. So it's already like super redundant, like you've got the super redundant encoding of your bit. It's almost like you've done like the classical repetition error correcting code, where you like take 1 bit and blow it up like times 1,000,000. So okay, if a few of them fail, or like go wrong, and you only have to correct things back to like the 0 or 1, doesn't seem so bad. All right, so I guess the computers we built today are super reliable, and we don't basically even worry about them just like randomly flipping a stray bit. Although from what I understand, they do it. It's just like maybe, I don't know, like computers today like satisfy a model like this, but maybe eta is like 2 to the minus 64 or something. So somehow it's not so bad. And even if like 1 bit gets flipped unbelievably rarely, it's often like not a big deal, things go on. So that's the practice of it. But then, back in the 50s, they were studying the theory of it. And von Neumann was the first to study it in 52. And he sketched the proof of a fault tolerance theorem, which was later made rigorous by computer scientists and so forth. And the theorem kind of looked like this. He proved there exists like a universal number, like literally eta 0, some actual constant number, such that provided your noise rate, eta, in your noisy circuits is smaller than this threshold, eta 0, you can make any classical computation fault tolerant. And also, it's like not too expensive. So if you have a classical noiseless circuit computing something with m gates, and you can use some kind of error correcting codes and fault tolerance scheme and get something like m log m gates circuit that computes the same thing with high probability, but is it can tolerate all the gates outputting garbage with some constant probability. And actually, that log m blow up you can also prove is necessary. You can't do without it. So that was, as I said, pretty satisfying in theory, but not used too much in practice. Except that until quantum computation came along, and people had to sort of think about this issue again. So with quantum computation, it seems like a lot trickier. So with this fault tolerance stuff, I mean, one basic thing you need is like error correcting codes, like a way to redundantly store your information. You also, on top of that, need like algorithms that compute on the error corrected information, and you have to worry about the fact that those algorithms themselves like are subject to the noise. But the first ingredient is error correcting codes, and Shor, actually, after he came up with his factoring algorithm in '94 or so, that's the first thing he turned his attention to, quantum error correcting codes, because I think he realized that this was a potential sticking point. And if you think about it first, it might seem implausible somehow that you could even have quantum error correcting codes for a few reasons. One, like with digital error correcting codes, classical ones, you're just trying to guard against a 0 or 1, so there's like a discreteness. Whereas in quantum, you're trying to protect these quantum amplitudes, which are like continuous. It also seems worrisome that you can't do like the simplest even error correcting code, it seems, like the repetition code, where you take a bit and you protect it by just copying it a bunch of times, because of maybe the no cloning theorem should prevent this. So that's worrisome. There's some other worry I had in mind too. Oh, well, normally in error correcting codes, right? Periodically you look at the encoded bits and you're like, uh-oh, it looks like this is no longer a code word. It looks like some corruption has happened. I'll now fix it. Well, of course, this is the thing you cannot do with quantum bits, right? If you look at them, that spoils them. It's like you've introduced error. So all of these seem like challenging issues, but turns out you can do it. And it's actually not even that hard. If we had a couple more lectures, I would have talked about it. Shor kind of came up with the first error correcting code for qubits, which is quite simple, actually. It has a property that, to encode 1 logical qubit, you encode it with 9 physical qubits. And it has a property that, you can store 1 qubit with these 9 physical qubits, and if a lightning bolt comes and zaps any one of them and makes it completely fail, you can still apply some quantum error correcting logic to it to get it back into the correctly encoded state. So that was pretty cool. Now, as I said, error correcting codes are not enough to do fault tolerance, because you actually have to also make logic that computes on error corrected data and is self-fault tolerant to noise. But yeah, shortly thereafter, following some of these ideas, they proved the analogous theorem for quantum. It's sometimes called the quantum threshold theorem. This was proved by Dorit Aharonov and her PhD advisor, Mickey Benor. And it literally says this: there exists some literal universal number, eta 0, such that provided, okay, the error rate for your quantum gates and qubits is smaller than this eta 0, you can make any circuit, let me add quantum circuit, fault tolerance. This log becomes polylog, but that's okay. Right, and it's the same kind of noise model. I mean, you can worry about the noise model, but basically the model is roughly like, for each quantum gate or each time slice here, there's some independent probability at most eta that the qubit turns into complete garbage. So even like a potentially a mixed state, not even a deterministic state, some adversarially created mixed state. Right, yeah.
Does the value of this concept not matter in either case?
No, it does matter. It matters a lot, yeah. This one, you mean?
Yeah.
Yeah, it matters a lot. So in their original work, this eta 0 was, they were like, well, it's something like 1 in a million. Which is okay, it's not like, okay, they're theorists, right? They could have put like 10 to the minus 10 to the 100 here. But it's like 1 in a million. Now that's still pretty small. I mean, this is like 99.99, whatever, 99 maybe % accuracy on your quantum gates. In fact, okay, so subsequently, people worked on this and came up with more sophisticated error-correcting codes, more sophisticated quantum fault tolerance algorithms. And currently these days, with the best error-correcting codes, the best fault tolerance algorithms, this eta 0 is more like in the range 10 to the minus 3 to 10 to the minus 2. Depends on things like what exactly the noise model is, what exactly the gate model is, et cetera, but something like that, which is interesting. Also, interestingly, it's not too relevant, but I want to mention it because it's interesting. There's a paper this year which was pretty cool by Fawzi, Gospelier, and Leverrier, building work by Gottesman, where they proved the same theorem with a much worse eta 0, but the blow up was just a constant factor, which was pretty amazing. Now you might ask, but Ryan, you told me that even in the classical case, it was proven that you need at least a blow up of logarithmic in order to achieve fault tolerance. That's true. So they did it in a model where your quantum gates experience noise, but your classical gates are noiseless. And so in that model, which is quite reasonable, they actually showed you don't need more than a constant factor blow up to achieve quantum fault tolerance. Now, yeah, so this is pretty cool. There's a real numerical threshold, literally, where if you get your quantum gates and qubits to have sufficiently high quality, well, if it's below this, then you're just going all your computation will just go to garbage after a short amount of time. But conversely, if you get your quantum gate implementations better than this threshold, then you can do arbitrary quantum computation of arbitrary length. So therefore, you of course may ask well, what I mean for the best experimental engineering setups that they have today, what kind of eta are they getting? And it's kind of like 10 to the minus 3. So then you may feel excited, isn't this great? Are we about to do it and have full-scale quantum computation? Well, as you might expect, there's some caveats. So, I mean, one caveat, there's several caveats. One caveat is that okay, there's a mismatch a little bit between theory and practice. It's the best theoretical algorithm. It's based on an idealized noise model. In real world, they have a different noise model, and probably the practical experiments, they're publishing their best numbers, oh, we got 10 to the minus 3, in this very carefully controlled conditions. So there's that. Maybe you would feel we need a few more factors of 10 to really cross the barrier. But there's still more problems. So one of them is, this threshold, the best threshold theorem, the theoretical threshold theorem we know, which has this eta 0 somewhere around 10 to the minus 3 or 10 to the minus 2. This is using the best known, most sophisticated error-correcting codes and fault tolerance algorithms. And these are kind of complicated. They're not insanely complicated, but they're kind of complicated. And they might have the property that to store one logical qubit, you maybe use 100 physical qubits. or at least a few dozen physical qubits, so let's say 100 physical qubits to encode it. And that's a little bit rough, so if you want to build a quantum computer with like 72 logical qubits or 100 logical qubits, now you need 100 times 100, 10,000 physical qubits all working together, in this like pattern to actually do it. So that's beyond what we can do right now. Another issue that I find like very intriguing is, again, with these best known fault tolerance algorithms and error correcting codes, there's a significant classical component to them. So like the way it works is like quite often you like do a quantum measurement, and that gives you some kind of like error syndrome that like lets you understand like, oh, now I have to apply some fault tolerance step to like fix things up. And the calculation of like, oh, given what you measured, like what step should you take to rectify things? It's purely classical calculation, and it's there's an efficient algorithm for it, but it's like a cubic time algorithm based on like min weight perfect matchings and graphs, which is not great in practice. And furthermore, the qubits are like decaying like so fast that you would have to run this classical algorithm like super fast, like maybe once every clock cycle or like once every 10 clock cycles, which is not feasible. So you could say, oh, maybe we should go back to like a less sophisticated fault tolerance algorithm where we have like a very simple like, I don't know, fault tolerance routines, but then that makes, the a to 0 like go back a lot worse, maybe back down to 10 to the minus 6 or 10 to the minus 8. And then it's like a huge engineering challenge to get like super high quality qubits and qubit gate implementations that get up to that level. So that's the caveats and the difficulty from what I understand. Not like a real expert here. Yeah. And in fact, as far as I'm aware, quantum error correction, not even quantum fault tolerance, but quantum error correction has never been demonstrated in practice, even like on a super small scale of like, oh, let's use like 6 physical qubits to like encode like 1 logical qubit for like a long time. As far as I know, even that has never been done. So we're still a long way from like actually, or some way away from like actually using this theorem to our advantage. But this is the desired end goal. By the way, feel free to interrupt me if you have any questions.
But is it never been done because nobody quite tried to do it, or because it failed?
I think it's perceived to be like too hard. I mean, you need to, I don't know, get like a somewhat sophisticated, maybe, I don't know, like 6 or 10 or 11 or 5 or something qubit algorithm, which itself has to last for a while. I think actually maybe they've maybe done like the simplest possible thing with like encoding 1 qubit kind of with like 5 physical qubits. But I think it's just hard. I mean, it was only like a few years ago that they were able to get like 6 entangled qubits cooked up like with like 80% fidelity from what they were trying to cook up. So it's tough. But as I said, on the other hand, I said, oh, they're going to try to achieve quantum supremacy soon. So what's that all about? Yeah.
Not to put you on the spot, but there's you probably know that some people, some like renowned scientists have like some opinion that like in practice you'll never be able to like make these things work. Like Ilkala has something about this.
Yeah.
So how does that like relate to all of these things?
Yeah, I don't exactly know what their argument is, so I'm not sure. I mean, the standard positive response, which I sort of believe in, is there's really like no currently conceivable like theoretical barrier to doing all the things we want to do. And therefore, if it turns out there is some like fundamental barrier, it must be due to some like new law of physics, like some new addendum to quantum mechanics. And that would be amazing. Like, I mean, quantum mechanics has been like safe and secure and like predicting every experiment for like close to a century. So if there's like some new like law of physics that came out of this, that would be super awesome and it would justify all this work on quantum computation. So it's kind of like win-win. Either it works or like, something super fundamentally new has to be the case. But I think, one thing that could go wrong is it just remains like a super hard engineering challenge for a long time. Like, oh, why haven't we sent humans to Mars and built cities there? There's no like theoretical reason we cannot do it, but it's very hard, right? So it could be like that for a while. Yeah, so okay, they're working on it though. And in particular, as I mentioned, this group, let's say at Google, that's trying to actually achieve this quantum supremacy, what are they actually doing? Well, they're going to like build a picture like this with like absolutely no error correction. It's going to have 72 qubits and like a 9x8 grid, maybe like 20 layers. And they're just going to be like, we're going to make our bestest, most awesome, high quality gates and just glue them together, no error correction, run them, hope it does something good. Yeah, so we'll see. So let me actually say a little bit more about details of this quantum supremacy plan that people are trying. Right, so you're not going to be able to do any useful computation with this circuit, but you're able to maybe do something with this circuit. And what that something is simulate a quantum circuit. And hopefully it'll be hard for classical algorithms to do the same thing. And actually that motivates why they're going to try to simulate a randomly chosen quantum circuit. So let me write a little bit the plan. So here's the plan. So let's say on paper, they're going to draw a random, oops, that's not random, quantum circuit that looks like this, which I'll call B for blueprint. Okay, so they're literally going to be like, all right, like we'll put for every qubit, like with some probability, we'll put in a 1 qubit gate that's drawn from some distribution, and maybe they'll leave some untouched, and maybe they'll put some C-naughts in random places, and they'll do it for like 20 slices, and that's it. So they'll just use some random coins to draw a picture of the circuit that they're thinking of. So let's call that B. Yeah, it's going to have, in their plans, it's going to have 72 qubits. Actually, in the original plans, it's going to have 49, 7 by 7. But then after they published that paper, many groups like IBM and like UIUC in China like quickly piled on to show that like you didn't think hard enough about like how you could really try to simulate this with a classical computer using all sorts of programming tricks and exponential time algorithms, but smart exponential time algorithms. And like in the last like year, there's all these papers about like, oh, actually we can simulate classically 49 qubit random circuits of this sort. So then Google's like, okay, fine, we'll do 72 then. Yeah, and like the layers is like 20. And so maybe the total number of gates is, I don't know, like 1,000 or something. Right, so like literally they'll draw that like on a piece of paper. And also, as I mentioned here, there'll be like a 1 qubit measuring gate at all the end. And also, like, don't think of it as having an input. Like, they'll just plug in zeros at the input. Okay, so they draw that on a piece of paper. And now, okay, so theoretically, there'll be some state that this particular blueprint circuit will get into here. And then they'll measure. So the measurement outcome will be 72 classical bits. And of course, there's randomness. So that will create, therefore, a classical probability distribution, which I'll call P sub B on 0, 1 to the n, or I don't know, 0, 1 to the 72. Okay, so just to be clear, this is a random procedure that creates a probability distribution. So it's like a randomly chosen probability distribution. There's 2 layers of randomness here. And then they're going to say, OK, here's the task. Build a machine, like in the physical world, that, I'll explain in words, but let's say samples P sub B. So build a machine. It'll have some internal randomness that when you hit the button on the machine, it outputs a 72-bit string. And the goal is that, every time you hit the button, it can output a 72-bit string. And the goal is it should output the strings with this probability distribution. Okay, and the designer of the machine gets to look at the blueprint B and try to build a machine that outputs strings according to this distribution. So notice it's not a decision task, which is what we've been talking about mostly in this course, and in particular yesterday in complexity theory. It's not like there's a correct output. The whole task is to like generate a probability distribution. Any question?
I thought that 72 was C, so I was really confused.
Oh yeah, no, somehow it's my 7. Yeah, bad digits. Okay, then step 4, I mean, this is where the quantum engineering comes in. They're going to try to build physically in the real world B, hopefully. Well, they're going to build something that's like, they're going to try, they're going to actually put the gates in and try to build it. And that'll be some like real quantum circuit, which I'll call Q, like it's physically extant. And then that Q itself will generate some probability distribution, P sub Q, on 72-bit strings. But due to like noise and like imperfectly constructed gates and so forth, PQ will not be the same as PB, presumably. I mean, if they could like literally perfectly 100% accurately copy this blueprint into real life, they would be the same. But that ain't gonna happen. They're happy to say. But they're gonna hope or try to get it such that, well, roughly PQ is approximately PB. Okay, we'll talk about this later. And then they're going to just assert that any classical randomized circuit C will give P sub C, which is not close to P sub B. So just kind of say that, like, well, there's no way you could build a circuit, even given the blueprint, there's no way you could build a circuit in real life, like an actual computer program, that will generate draws of 72 bits that will look anything like this probability distribution P sub B. Yes?
If they don't have a classical circuit and they don't know that their PQ works, how do they know that their PQ is like PB?
Oh yeah, that's a good question. We'll get to that. That's a good question. And then the last step is profit, or declare quantum supremacy and collect their Nobel Prizes or what have you. Right. What's particularly funny is they're quite clear in the paper that they're not really hoping, building a quantum computer is very hard. They're not really hoping that PQ will really be close to PB. In fact, they fully allow that PQ will actually be quite terrible implementation of PB. They're just going to be arguing that, any classical circuit will be even more terrible at sampling PB. So, that's the task. Slightly non-terribly build a machine that samples PB. Was there a question back here? Yeah?
So I think you said that when Google announced that they're going to do it for 49
Yeah.
qubits, people came out with classical algorithms that does do it. What makes increasing the number of bits that different?
Well, I mean, as we talked about yesterday, you can have a classical algorithm that will say compute the entire final state here. Now, even to write it down, literally requires 2 to the, let's say if it's 49, 2 to the 49 numbers. That's fine, right? How big is 2 to the 49? It's not that big. It's maybe that's some terabytes, some thousands of terabytes. I don't know. That's okay. But 2 to the 72, it sounds funny, but that's not so fine. That's a lot bigger. So then you'd have to get into things I can't explicitly store it, but maybe I can make an algorithm that will find the large amplitudes, or it'll return a desired amplitude, on request. It's this is really right the barrier where you can go from conceive of running exponential time algorithms to not conceive of them. And initially they thought, 2 to the 49, that should be safe, because okay, it's not really 2 to the 49, maybe it's 4 to the 49 time, which makes an enormous difference, right? And so forth. But they didn't, naturally if you're them, right, you don't probably put 100% of your effort into trying to break your own paper, right? So trying to really design the cleverest possible classical algorithm that takes advantage of the full geometry here and partitions this up and super smart to try to shave running time off. But of course everybody else is motivated to do that, so they do that. And actually, to be fair, now they themselves are writing papers about how you can do that. And so actually funny, the last Google paper, I really loved it because instead of reporting the running time of their algorithm or the space usage of their algorithm, their measure of efficiency was dollars. So they're this is how much it would cost you. like, I don't know, cloud services to like, do this for like more qubits, which I was like, oh, actually that makes sense. Yeah, so hopefully they think 72 is safe, but then, I mean, it's okay. It's like, I don't know, whatever, 25% harder or 50% harder to build the qubits. Yes?
So why does this have to be random? A random circuit?
Oh, well, there's two reasons. But the main one is they want to try to assert that it will be hard for a classical computer or algorithm, like staring at this blueprint, to produce the output distribution. And if you want to like make a hard circuit, a challenging circuit, I guess they're like, well, like it shouldn't have a special structure because maybe that could be exploited. So like our best bet is just like pick it randomly. Actually, that's a good question though, because in particular I want to ask think about what do we feel, or what do they feel like this PB will look like. There's a phenomenon in math that like when you choose a large object at random, it's sort of not random. It's a little bit deterministic what it will actually be like. Okay, so the question is like, what do we feel this distribution will look like? This theoretical distribution. So, okay, one thing is like this whole circuit is one giant unitary, U. It depends on B, and of dimension 2 to the 72. And the first thing that they posit is that U, when B is chosen at random, U sub B will be similar to like uniformly random unitary. 2 to the 72 dimensional unitary. Okay, it's not hard, even though it's not hard to make sense of that mathematically. It's basically like a unitary is sort of like a rotation, right? So like just a random rotation. Now it may seem intuitive that if you put like more and more like gates in randomly, the overall unitary should start to look like a random unitary. And nobody knows how to prove that, although it's a clean mathematical question, and people can try to prove it. And in fact, over the last few years, there have been like theoretical papers going towards justifying this, statement star. Like there's a paper this year by Harrow and Mehrabin that showed something like this, that if you take an n qubit circuit where the gates are arranged in a grid and you put in random 1 and 2 qubit gates, maybe not like exactly how Google said they're going to do it, but like in some reasonable way, and you do it for big O of square root n layers, then the resulting unitary will be kind of close to a random unitary in some metric. So it's like a positive result towards justifying this star. Whether or not you think 20 is the square root of big O of the square root of 72, it's up to you.
When you say big O, you mean at least for that, right?
Yeah. Yes, yeah. I mean, in particular, like it kind of has to be like these. In general, this will be like root n by root n grid of qubits, and like there needs to be like at least root n layers, kind of. Since the 2 qubit gates like are only going in adjacent pairs, like in order to like have the first qubit have any chance of interacting with the last qubit, like you need at least root n. And the conjecture is that root n are sufficient, and they have some positive results towards this. So essentially, this assumption star is kind of the least of people's worries right now. It seems kind of reasonable. Okay, so that's the unitary. So you might ask, what does a random unitary matrix look like? That's very easy to understand by mathematicians. And, well, actually, let me draw one more thing. So this unitary looks like some gigantic 2 to the 72 by 2 to the 72 dimensional matrix. And then the state here, right before you measure, is this unitary applied to the all zeros ket. The all zeros ket, as you know, is this one, 1, 0, 0, 0, 0, 0, with 2 to the 72 minus 1 zeros. And therefore, the final state here is the vector this times this, which is just this column. Okay? So the final state, if you make the ansatz that this is a random unitary, the final state here is distributed like the first column in a random unitary matrix. And mathematicians easily know what that looks like. They know that it's very, very, very closely approximated by what you would get if you just picked random Gaussian random variables for each entry here. Okay, there should be complex Gaussian random variables, and the normalization should be such that the total variance is 1, because the sum of the squares of the entries in the column of a unitary should be 1. Right, but they're basically distributed like independent Gaussians. That's an easy mathematical fact. And OK, then there's like this last step where you measure and like PB comes out. And what are the probabilities? Well, it's the squares of these amplitudes. OK, and what is the square of a Gaussian, or the magnitude squared of a Gaussian random variable? If you may know, that's an exponential random variable. And therefore, the expectation is that for each x, the probability of outputting x will be distributed like an exponential random variable over capital N. And independent exponential random variables for each x. So exponential random variable is a random variable that's non-negative. Its mean is 1. And I don't know, its PDF is like e to the minus x. So yeah, it's a random variable. It's a little bit bottom heavy. It like tends to be less than 1. But because it has some like modest probability of being bigger than any number bigger than 1, it averages out to have mean 1. So this is vaguely like a uniform distribution in the sense that each probability is kind of like a constant over n, but it's not like all the constants are 1. That would be the uniform distribution, like 1 over n for every string. It's like imagine you created a probability distribution. Remember, this is a randomly constructed probability distribution where all these numerators were independent exponential random variables. So this model of a random probability distribution has a name. Apparently it's called Porter-Thomas distribution on distributions. And yeah, as I said, like it's vaguely like a uniform distribution, but some elements, are like heavier and some elements are lighter. And you kind of know, everybody kind of knows that the final distribution here will be like this Porter-Thomas distribution, but like you don't know which are the heavy elements and which are the light elements. Those are like, randomly arranged due to this nature. And you can try to look at the blueprint B to help you out, but it doesn't seem clear that this can help you, especially if you're a classical algorithm. Yeah, so that's the task. And even the quantum algorithm, it's not clear that like it can like compute these PB of x's, but it can just, ideally like run itself and it'll output from this blueprint, it'll output according to this distribution P sub B. Okay, any question? Yeah.
So we can check if the output is distributed like a Porter-Thomas distribution.
Good. So this is exactly related to the last question you asked, which is what I'll get into now, right? So, good. So how are you going to evaluate these things? Okay? You kind of know that this PB will be some Porter-Thomas distribution. But how are you going to evaluate, mainly, how are you going to evaluate this, the claim that the physical object that you built, which you can hit a button and it'll output a 72-bit string, whether it's close, quote unquote close to this distribution, and a little bit like, why might you assert this, or how can you compare to a classically generatable distribution? So, in my opinion, this is kind of a statistics question, and the most natural, I think, / correct way to evaluate a distribution uses the KL divergence. This is some measure of distance between probability distributions. Okay, so let me write, if you have some probability distribution P, which you mentally kind of think of as like the true distribution, and some probability distribution P hat, which you mentally think of as like an attempt to make this distribution or a hypothesis for what this distribution is. The KL divergence, this is like a number. It comes up in information theory. It's related to entropy. It has a formula. It's this: sum over all strings x, p of x, log, well, that's natural log, I guess. I'll write ln, p of x over p hat x. Okay, so this is like the rate for a given x is like the ratio between like maybe the true probability of x and the hypothesized probability of x. And so ideally this will be close to 1. So when you log it, ideally it'll be close to 0. But it might not be. And so you measure the average score here for a string x drawn from the true distribution. So let me just say this is like a well-studied concept in statistics and so forth. It's a number that measures how similar these two distributions are. It's non-negative, and the bigger it is, the less similar they are. It's also not symmetric, by the way. Okay. And so ideally, I believe, you should try to compare two things. You should try to compare the quote-unquote true distribution, p sub b, versus the one that your quantum circuit outputs. And hopefully this is small. And then hopefully it's smaller than what you would get for, let's say, a classical distribution, PC. Like, by which I mean any distribution that you can generate by a classical computer. Now, actually, in their paper, they kind of get their stats a little bit backwards, in my opinion. And actually, I understand why they do it. It's for some difficult real-world reason that's related to your question that I'll get to. But in my opinion, they kind of, I don't want to say messed this up a bit, but it's a little bit backwards in their paper. That's what I feel. I mean, John Martinis, if you're watching this video, call me. We can talk. But just for a second, let me talk about this way, which I think would be the most natural way to try to understand the quality of an algorithm. So one thing that they sort of boldly assert, and it's reasonable, maybe, and we'll kind of end the class by talking about this bold assertion, is that this task is very hard for a classical algorithm. You get a quantum blueprint, you have polynomial time, what are you going to do? Basically, the assertion is that there's basically nothing you can do. And therefore, your best bet is to just output the uniform distribution. You can at least do that. That's easy, to make a machine that outputs the uniform distribution. And perhaps it's not terrible. I mean, obviously, it's oblivious. It doesn't even look at the circuit. But it's vaguely comparable to this distribution. So they basically just kind of say, well, we're going to assume that that's what a classical computer can do. So let me write the uniform distribution here. And now you can actually calculate this. Because this capital N, I should have always said this capital N is, as usual, 2 to the little n. With high probability, you know what this PB will look like. You can do a very simple calculation based on the exponential distribution. And this will, with very high probability, equal a fixed number, which is gamma, the Euler-Mascheroni constant, which is like 0.577. This is like the difference between the nth harmonic number and ln n in the limit as n increases. So that's that. And it's kind of reasonable. At least, OK, it's not 0. These are not the same distribution. It's not insanely large. This actually, the KL divergence in general can be infinite. Or it can depend on capital N. But this is medium. It's a modestly small number, 0.577, which is reasonable. So in some sense, you can read their paper as saying, well, our whole goal in life will be to build a physical implementation Q of this blueprint B, and then try to justify that this is at most 0.56, and then we'll be done, quantum supremacy. Because you did the task a little bit better than any classical computer can do it. Yep?
Wait, how do you calculate PV in the first place?
Yes, exactly. This is, again, also my question a lot as I was reading this for the first time. What are they thinking here? Indeed, in particular, they're going to probably strive to do better than that. They're going to maybe try to get this really close to 0 or maybe 0.1 or something. So there's a legit gap here. But this is at a high level their plan. OK, so now we got to ask ourselves, how are they going to judge this at all? And they're well, we have several ideas. One is they're well, we have some very vaguely justified heuristic computations that say, like, if you know the exact noise rate eta for your actual physical implementation of each gate, you can sort of justify like an overall calculation of what you would expect this to be, and it becomes smaller if eta is small enough. So like that's one thing. They're like, oh, if we can get eta to be real small, which is easy to like reason about, then this should be small. Now you would prefer to have like some experimental demonstration that this specific figure of merit is small, so they like talk about that too. There are several problems here. One, you don't really have access to this distribution, P sub q. Well, it's not like you got it written down. You can press a button on your physical machine to get draws from it. You also don't have access to P sub b. In some sense, that's literally the whole point, that this is supposed to be like classically uncomputable. However, let me face the other problem and just assume that you have classical access to P sub b, which does seem like a catch-22, but just bear with me for a second. So I'll justify it a little bit according to how they're thinking about it, because there's still problems. Let's assume you literally like knew P sub b for your blueprint. And how are they planning to get around this? They're like, well, there's a couple things. You can do this whole story with 25 qubits first. And then 25 is small enough that you can just literally, it's not a problem to calculate P sub b explicitly. And then you can try, with things I'll talk about in a second, to estimate this, and like hopefully it'll be like 0.1 or something small, and you'll be like, that's great, and it was consistent with my heuristic about like my noise rates and so forth. And then you can try n to be 36, and maybe that's fine also to compute P's b explicitly, and like again, like check that this is kind of small and it's consistent, and like maybe make like a graph and see like, oh, even for n equals 49, like maybe we can do that these days. And like if it's looking good, then you'll just sort of assume that like, hey, for n equals 72, it should also be good, right? It's not so unreasonable. I mean, you got to do something. You can also use some other tricks. One thing that they suggested, which is nice, is it's an interesting fact that if you have a quantum circuit with C0 gates, and your 1-qubit gates are only like Hadamard gates, or Hadamards and not gates, you can classically compute the final state distribution. That's actually a non-trivial theorem. It's kind of an interesting theorem, efficiently. And therefore, they're like, hey, we'll also do some experiments where we like only use like Hadamard gates and not gates. And then we'll be able to like, and you can do that with n equals, I don't know, 72. And then we'll be able to like actually get a classical handle on PB. And we can test the experiment that way, even though we don't expect that it's actually hard. I mean, we know it's not actually hard, but it'll help us give it a sense of like how good our implementations Q of B are. So that's some things they're thinking. It still leaves out another difficulty, which is, we don't have access to P sub q really either, except through experimentation. And imagine now that you literally know P sub b, like that's not a problem to you. But let's look at this formula. If we plug in P sub b and P sub q here, this will be P sub b, this will be P sub b, this will be P sub q. And imagine, you can, for every x, you can compute P sub b of x. By the way, there's 2 to the 72 x's. So like you cannot just do this sum. That's one problem. And even if you somehow, like 2 to the 72 weren't that big, like you have an x, and you'd be like, now I want to know what is the probability my quantum machine will output that x. What are you going to do? So they're kind of like, well, let's change the formula. Let's change our definition of what you're trying to do. Let's change the figure of merit. And this is where it gets a little bit into the backwardness. And in some sense, like the first thing they do is like reverse this. So like look at PQ versus PB. As I said, it's not symmetric. So this is really not the right thing to do, because like now this is sort of supposed to be the true distribution. This is the approximation. But OK, fine, let's leave it at that. And then that's still a problem, because if you switch these, like PQ, PQ, PB, well, you can't easily get at this either. Maybe it's getting closer, though, because this sum over x, P sub q of x of something, this looks like expectation over x drawn from the quantum circuit of something. OK, so you could write this as like expectation over x drawn from PQ of this quantity. And in some sense, this you can get at experimentally. You can like hit the button on your quantum machine. They're like, we could do it 1,000 times or 100,000 times and get samples from P sub q. So if we could numerically compute this, we could kind of just take an empirical estimate and see how good things are. And they're willing to assume that they can compute this, but they still have the problem they cannot compute this. So they're kind of like, well, let's change the formula again and like call the thing that we're shooting for cross entropy. Or cross entropy difference, and basically they just say, okay, we're going to make our, a measure of goodness, this expression. I don't know, they call it delta H or something. Yeah, something like this: expectation over x drawn from PQ of, ln of 1 over P sub b. Okay, which is not the same as this, but, well, it's something. It has arisen in statistics. And finally, now, this is something that they can, of x, empirically estimate, assuming they can compute B sub b. Right, they can draw like a bunch of samples from their quantum circuit, and for each one, like, run their classical supercomputer to compute P sub b of x, and take an empirical average. And this is a quantity that like potentially becomes bigger the more aligned P sub q is with P sub b. Yeah?
How likely are they to get the same sample twice, assuming that this recursion?
Hopefully extremely unlikely, right? Because if they're doing like a reasonable-ish job, P sub q will look kind of like this, and n is like 2 to the 72. So like they should presumably never get the same draw twice. Yeah, I think this requires a lot of thought. Well, the hope is that like this is not the uniform distribution. It's got some heavy-ish elements and light elements, but yeah. So right, actually, we can actually dive into this like a little bit. Each P sub b of x here looks like this. It's like some constant, maybe c of x over capital N. So this will be like, okay, it's the reciprocal of that. So this is like n over, well, what I was calling c sub x. That's coming from P sub b. So if you write this as ln n minus ln cx, then you can just bring the ln out. So like you'll ln n out. So you'll have some additive ln n here, which will be the same for any distribution. And therefore, you can basically ignore it. So therefore, you can sort of only think about this as your figure of merit, where this cx is like the numerator in pbx. Okay? And so you see, for the heavy elements, the ones where cx is large, this will be, have I done this right? Let's see. This will be negative. Oh, maybe I put a subtraction in. It's somehow, maybe I'm mixing it up here. You want, you're hoping that this sample here will give you, probably if you want to maximize it, I don't know, maybe I mixed something up. It should be like this. Because you want that like your samples, if this is similar to PB, it's like you're getting draws, you're biased towards the draws where this CX is like a little bit large. Okay, and therefore like you expect this quantity to be a little bit large. And actually, you can compute what this quantity would be if P sub Q were exactly equal to P sub B. And I think it's like 1 or something. Whereas you can compute what this would be if you just use like the uniform distribution on the assumption that like, oh, the uniform distribution is the best thing that like a classical algorithm could do. And it's some other number which is like 0. Maybe I got the additive constants wrong, but there's some gap here. Maybe there's some gammas involved. So their story is they kind of say, okay, this will be our final figure of merit. We can estimate this empirically. We know that if PQ were exactly equal to PB, it would be this one larger number. If a classical algorithm is just throwing up its hands and saying, oh, I'll use the uniform distribution, it'll be a lower number. And so if they can just show that like, the thing they actually get with this PQ is like a little bit bigger than 0, they'll be like quantum supremacy. Although I was thinking about it, and there's something funny, or maybe even a little bit fishy here, with this figure of merit, because it has the property that the optimal distribution, if you're trying to like generate a distribution here which maximizes this expectation, the optimal distribution is not p sub b. So you can actually potentially do even better than you're like supposed to do. In fact, the optimal distribution is the one that puts 100% of its probability mass on p sub b's most likely element. And that'll have the property that this quantity is like little n, which is like way bigger, which is kind of weird. So maybe trying to build a classical algorithm that makes this particular figure of merit large is not exactly what the task you would think it is. Maybe you're not trying to like match p sub b so well as just discover like one heavy element, and like that'll help you do a good job at beating this test, statistical test. So that's why I'm like a little unsure about like the story that I have here. On the other hand, from their point of view, you do face this difficulty, which is that if you try like these statistical things that are like the more correct thing to measure, like it's not clear how you're ever going to measure them. And like this is like the one thing that's kind of like a reasonable measurement that you can estimate empirically from samples from your quantum circuit Q. Yeah?
I'm kind of confused. Like, are you assuming that p sub b is like equal to that exponential n thing?
Yes.
How reasonable is it?
Yeah, that is, I think, the most reasonable out of all the assumptions here. So, I mean, there are like theoretical results towards that fact, and there are simulations. Like, you can just like simulate this for like n is 25 or 36, and try to confirm this fact yourself. Actually, feel it's a little fishy if like you really don't make this depth very high. It might not be accurate. Like, if you believe that this is what the distribution is, right? Like this is like really saying that like every single string, of which there are 2 to the 72, has like a non-zero probability that's kind of in the neighborhood of constant over n. Like that's, I don't know, the circuit has to be kind of quite mixing if that's like every amplitude, for example, is going to be non-zero, I would have thought. But anyway, I think this is somehow still nevertheless considered the safest part of the story. Right. So, yeah. So this is stuff to think about. And like it kind of changes what you're trying to measure here, like how you're judging the closeness between distributions actually affects, I think, maybe what your belief should be about like how well classical algorithms can try to score on your metric. Like I'm not so sure like the idea of like, oh, the best thing it could do is output a uniform distribution is the best. So the last thing I want to talk about is this question as like a complexity theoretic question. To what extent do we have evidence that it's hard for a classical randomized circuit, to simulate the output distribution of like an explicitly given quantum circuit? And although in the quantum supremacy experiments, this will be like a randomized circuit, a randomly chosen circuit, well, the theory of average case complexity is less well developed. So let me switch gears a little bit and talk about the worst case version of this problem. Like just somebody gives you any quantum circuit diagram, and classically, you have to try to build a classical circuit whose output distribution matches what we would call the PB of this quantum circuit. And actually, that's not a fair question to match it exactly. So you should relax the question out of fairness. Insist only that the quantum, or the classical algorithm, let's say, approximately generates the distribution. Because on one hand, like even the quantum circuit, is probably going to have some noise and not going to accurately estimate itself. Also, just asking for like exact probabilities almost doesn't make sense. Like if, I don't know, the quantum circuit gets to use like unitary gates that have like a 3/5 in them, and then like the probabilistic machine is like, oh, I only have like coin flips. Like I can only generate probabilities that are like integer over 2 to the power of something. It's not fair, right? That it has to exactly get something with a denominator that's 5. So you should, have some notion of approximately matching the distribution. And perhaps the most reasonable notion is like the classical circuit or algorithm, given the blueprint, should generate a distribution that's close in, let's say, KL divergence to the output of the quantum circuit. But because I want to tell you some positive results about negative results, some like hardness results, I'll think about like a slightly stronger version where like it's a bit demanding on what the classical algorithm has to do. So let's say that we consider the following sampling task. You know, given like B, the blueprint of a quantum circuit, you know, generate a classical circuit, C, such that, let's say PB and PC are close, and I'll choose this. I'll say that PC of x, PB of x over PC of x is between, I don't know, 0.9 and 0.1. Okay, so what I'm saying is for every string x, the probability that your classical circuit outputs is within like a multiplicative factor like 1.1 of the true probability. So this is pretty demanding. It's like stronger than this, right? In like KL divergence, like you look at this ratio, which is supposed to be near 1, and you log it, and you take the expectation over some distribution on strings. Here it's like a worst case thing where you're like, oh, I want every string to be output with the correct probability up to some multiplicative constant. That's pretty challenging. In particular, it means you have to even get the really small probabilities right. Like if the theoretical quantum computer outputs a certain string with probability, you know, 2 to the minus square root n, like your classical circuit better output with probability 2 to the minus square root n times or divided by 1.1, which is strict, but okay, that's kind of what it's kind of what the quantum supremacy assumptions or assertions are all about, asserting that this task is impossible. So it's kind of like, I mean, just to use some fake letters here, it's like, you know, approximate sampling BQP versus approximate sampling that can be done with a classical computer BPP. So we're interested in this question. You know, can classical computers approximately sample the same distributions that quantum ones can? And it would be really great for this, you know, quantum supremacy program to like shore this up and like have some complexity theoretic evidence that this task is impossible. Well, as you know, in complexity theory, we cannot prove anything. So it's too much to ask that we, you know, show that this is impossible. But we have, after all these years, like a gold standard for complexity theory evidence. That's like showing something is true, assuming p does not equal np. So if we could have a theorem that said p does not equal np, implies that this is like not real terminology, but like approximate sampling in BQP is not the same as approximate sampling in BPP, we'd be like, this is as satisfied as we could get. You know, everybody believes p does not equal np, so this is our best evidence. This is the gold standard. I mean, it's like the whole theory of NP completeness. We say that, oh, there's no efficient algorithm for solving 3 coloring because it's NP hard. You know, if you assume p does not equal np, then that's true. There's no efficient algorithm for 3 coloring. So that would be great. Unfortunately, we don't know how to prove this either. But what we can prove, it was proven over, I don't know, sometime in the last 10 years, is like the silver standard of evidence instead of the gold standard. So instead of the gold standard, p does not equal np, we use like a stronger assumption, but still a cherished one among complexity theorists, which is that the polynomial time hierarchy doesn't collapse. So I'm not going to say what that means, but if you've taken complexity theory, you know what it means. In short, there's like this hierarchy of complexity classes like p, np, there's also co-np, there's something like p to the np, there's like np to the np. This one is also called sigma 0. This one's called sigma 1. This one's called sigma 2. There's like np to the np to the np, whatever these things are. That's sigma 3. And then it goes higher and higher and higher. And this whole thing, this very large complexity class is called, that includes all of them, is called polynomial time hierarchy. And to say that p equals np is to say that these two classes are the same. We highly don't believe that. And to say that polynomial time hierarchy collapses, the negation of this, is to say that some of these classes are the same. Or that like all of these classes become the same as like one of these sigmas. So this is an assumption which is stronger, strictly stronger than p does not equal np. Like, we've thought about it since like the mid-70s, and we're like, we feel like pretty happy if we show, under this assumption, a theorem. We're like, this is pretty good evidence as far as we know. And this is a theorem, which is pretty nice. I mean, it gives some, complexity theory status to this assertion, even though it doesn't exactly match up. And this was sort of proven in stages by a variety of people: Barbara Turhall, David DiVincenzo, Scott Aronson, Michael Bremner, Richard Joza, Dan Shepard, a paper of Arkhipov with Aronson. And I'll tell you a little bit about it. And that'll be the last thing we talk about. And what's fun about this theorem is the proof of it involves time travel. So it's a great topic to end on. So let me tell you a little bit about time travel and how it relates to this theorem. I'm going to sketch the proof of this in the contrapositive. So the contrapositive is this. If every quantum distribution could be very well simulated by a classical distribution, then the polynomial time hierarchy does collapse. So what we're going to show is that if this simulation fact is true, then actually this gigantic complexity class can be put inside a very small complexity class. I think this one, sigma 3. OK, so what does time travel have to do with this? OK. There's a concept called a closed time-like curve. And what is a closed time-like curve, briefly? It's a point in space and time and another point in space and time, usually the same space point but different time points, where by definition, let's say one bit can fit in this point in space. By definition, the state of this bit in this point in space-time is the same as this bit in space-time. That's like the definition of a CTC. I'll talk about it slightly more in a second. But a fellow you might have heard of called Kurt Gödel in the 40s proved that the existence of closed time-like curves is consistent with Einstein's laws of general relativity. So he didn't prove that space, these wormholes exist, but he proved that, they don't definitely not exist, right? They're consistent with the laws of physics as we know them. So that's neat. Then actually, Stephen Hawking and some other physicists whose name I forget kind of argued, well, they can't exist. They cannot exist. And they're like, we'll tell you why. This is supposed to be, let's say it's big enough, this point in space, to contain one bit. So they said, check this out. What if you just put a NOT gate here in space-time in between? And then they're like, we have an impossibility. If this bit is 0 at this point in space and time, then it's 1 here because it goes through a NOT gate. But that's not allowed because by definition, this is supposed to have the same state here and here. And on the other hand, if this bit is 1, then it would have to be 0 after through the NOT gate here. But 0 is not equal to 1. Contradiction. These wormholes cannot exist. And then one of our top heroes, the 10 to the 500 universes guy, David Deutsch, co-founder of quantum computing, was like, not so fast. You didn't think it through. Because he says, the laws of nature are quantum. And the true state of a quantum particle, or a bit, is a quantum state, which is inherently randomized. In fact, it's like a density matrix. You have like a little 2x2 density matrix here. And so it can have a randomized state. And actually, for this little NOT gate, you don't even need quantumness. He just said, you didn't think of this case, Hawking. The state of this bit is 50% chance of 0, 50% chance of 1. And now check it out. If you pass a bit in this probabilistic state through a NOT gate, well, you get 50% chance of 1 and 50% chance of 0, which is the same thing. So it is possible. And more generally, if you have a quantum circuit here, he basically observed that whatever it is, there exists a density matrix, which is a fixed point for this quantum circuit. And therefore, it would be consistent with everything if just the state of the particle here were that fixed density matrix. So then he's like, as he did exactly with quantum computation, how could we use this to our advantage? If wormholes existed and could be found, what computational advantage could it confer if you could send bits back in time? He wrote a paper about this. And interestingly, it took some papers to think about this. One thing it depends on is how many bits you can send through time. Yeah?
Question. It's like, what this is saying there exists a particle in some state which can be consistent within a wormhole.
Yes.
But if you imagine a wormhole as kind of like a hole in which you can put any particle, then that's not consistent. So what is exactly this time travel wormhole means?
Yeah. Basically, the theoretical model, which I think you can tell a story, a physical real-world story about, is once you identify this wormhole, you can like I always like to think of it as like a microwave. Like the bit is inside a microwave. Like in the morning, you put a bit, you open it up, or you put a bit inside the microwave. Or sorry, you open up the microwave, a bit comes out. You put it through a quantum circuit of your choosing, and then you put the output back into the microwave, and then ding, it like goes back in time. And so basically, the way the model works is, based on what quantum circuit you put here, nature automagically sets the bit or bits that come out of the microwave to be in the fixed point state of your circuit. And then you can use that fact in your computation. So like somehow you can cook up a quantum circuit, and it's computationally challenging to find the density matrix, which is the fixed point of this quantum circuit transformation. But like the power of these CTCs is that they like automatically give it to you. So that's like kind of the theory model. This is why I like study this. I mean, okay, nobody's going to find a wormhole or whatever, right? But like, it's an interesting question. What is the computational complexity of finding the density matrix, which is a fixed point for a given input quantum circuit? And like in this model, like just the model is you automatically get it. Like we study non-determinism and other crazy things, so why not study this? And then you can ask, well, what computational advantage does that confer to you? And as I said, the answer depends on like how many bits you can send through time, travel through time. If it's polynomially many bits, then Aronson and Watrous showed that the power that you get is p-space. Exactly. So you can solve any problem in this big class p-space, but also no problem beyond p-space. So you can't solve every problem, but you can solve something. And actually, you can do that even if you only can put classical computers inside the microwave. And then my friend Jamsai and his student Abuzar Yakar Yilmaz were like, come on, man. A wormhole that can send polynomially many bits back in time, that's crazy. Let's only think about sending one bit in time. That's much more realistic. So you can ask, what is the power of these closed time-like curves if they can send one bit back in time, one classical bit back in time? And it can be shown, actually using results of Aronson, that this power, let me just say CTC1 added to quantum computing, gives you this crazy class PP that we talked about last time. So we showed last time that BQP is contained in PP. And if you augment the quantum computation with the ability to send one bit back in time, theoretically, you get this class PP, which is a funny class. It looks like this. On the other hand, you can ask, what power do you get if you're allowed to send one bit back in time, but you only can put classical machines into this time-traveling scenario? And unlike in the case where you could send polynomially many bits back in time, you get two different answers. This turns out to be like a very little-known class that was invented in the 80s in some obscure papers called BPP path. And suffice it to say, it's somewhere inside this polynomial hierarchy. It's like not a very large class. And an observation made by Bremner, Josa, and Shepard, it's a very simple observation. It was kind of like missed by Aronson when he made this observation, is that if you could, for every quantum circuit, you could replace it with a classical circuit that sampled the same distribution very closely. And it's important that it has to be very close, that like multiplicatively close. Then that strength of sampling the distribution is enough that would show that like the time traveling versions of it would give the same thing. So in particular, if this assumption holds, every quantum circuit's output distribution can be simulated very accurately by a classical distribution, you can show that the time travel amplified version of the class equals the time travel amplified version of BPP. And therefore, these two classes would be the same under this assumption. And then finally, classical complexity theorists already knew that this would cause the hierarchy to collapse, because this for the classical complexity lovers, like even though PP is a small class, if you look at P to the PP versus P to the BPP path, this is all some crazy nonsense, but it's a proof. This class is still small. It's contained within this small part of the hierarchy, sigma 3. But by Toda's theorem, this is like an enormous class. It contains the whole polynomial time hierarchy. And therefore, if these two things were equal, it would be extremely unlikely consequence these complexity classes would collapse. And therefore, we get the contrapositive of the thing they're trying to state. So that's basically where I'm going to end. It was kind of, I really enjoy the fact that at the end, like, you know, we got back to David Deutsch and his crazy ideas. And instead of parallel universes, we got to the equally delectable topic of time travel. And yeah, so there's many more things we could talk about. I wish we had more lectures, but we don't. So I'll stop here, and I hope you enjoyed learning about these topics.